This is review video 38, Thermodynamic Favorability. So first of all, what is it? It's also known as spontaneity, and you're going to see those two terms used pretty much interchangeably, no matter what source you happen to be looking at. The AP test might call it thermodynamic favorability or spontaneity, but they mean the same thing. And really, it's a question. And that question is, will a reaction or a process proceed under the given conditions without any outside intervention? So, will these two chemicals react? Will that thing change phase without you having to do anything to it? Without you having to heat it up, without you having to stir it or shake it or whatever. A reaction or process is considered favorable if it will spontaneously, naturally react or do whatever without you having to do anything extra to it. And a reaction or process is unfavorable if you need to do something to start that process going. It's going to depend on a couple of things. Specifically, favorability depends on the enthalpy change going on, so our delta H value, our entropy change, or level of chaos, our delta S value, and the temperature surrounding whatever that system happens to be. A process or reaction is likely to be thermodynamically favorable if it releases heat overall, so it has a negative delta H value, and it gains disorder or chaos over time, so it has a positive delta S value. But this does not mean that only exothermic negative delta H and positive delta X reactions are thermodynamically favorable. Oftentimes, there's a lot of things that are favorable and a lot of things that are not, and it really kind of depends on your circumstances because, again, you have to consider temperature as well. So there's this very helpful little chart that kind of gives you an idea if a process is likely to be a favorable or unfavorable depending on your circumstances. So if you have a reaction or process that has a positive delta S value, so it is endothermic, and a negative delta S value, meaning it's becoming more ordered over time, then that thing is probably going to be unfavorable, meaning that you're probably going to have to heat it or stir it or shake it or do whatever to get that reaction started. However, if we see the opposite, if we have an exothermic reaction that is gaining chaos or becoming more disordered over time, then that thing is usually going to be favorable and you will not have to do anything special to get it started. If we have a reaction or process that is exothermic and that thing is losing chaos over time or it's becoming more ordered, then it's really kind of dependent on temperature. So at a low temperature, that particular reaction or process is favorable in all likelihood, but at a higher temperature, that reaction or process is likely to be unfavorable. And again, this is not like a hard and fast rule. It's just what is likely to be true in this chart. There are exceptions to all of this, but it is likely that that thing is favorable at low temperatures and unfavorable at higher temperatures. If we have the opposite, if we have an endothermic reaction that is going to become more disordered over time, then at lower temperatures that thing is likely to be unfavorable, and at higher temperatures that thing is likely to be favorable. But again, I would like to stress that that does not mean there's no exceptions to this, because this is not a hard and fast rule. This is just a trend. Okay? So the way we really tell, the way we figure out whether or not a process is spontaneous is through an analysis of what's called Gibbs free energy. And Gibbs free energy is really a numerical measurement of thermodynamic favorability and how much energy in any process is free and available to do work. Delta G value is the value for Gibbs free energy, and it is measured in kilojoules per mole specifically. Here's your rule. If your delta G value is negative, that means that process is favorable. But if your delta G value is positive, then that process is unfavorable. This formula right here is the one that we use to figure out whether or not delta G is negative or delta G is positive. And you can see that delta G is dependent on our enthalpy value, our temperature, and our change in entropy. All right? So comparing that formula to a chart like this, you can kind of see where these trends start to pop up. So let's just plug in some numbers for fun. Let's make up some numbers and let's see what happens. So let's take this first situation here, the one where we have a positive delta H value and a negative delta S value, right? So let's say our delta H value is 1. And let's say our temperature is 1 Kelvin. And our delta S value is -1, right? Let's make everything super, super easy so we can see what happens to our delta G. If I work out that math, right, that means that I have 1 minus 1 times -1 is -1. Whenever I subtract a negative, I'm really adding a positive, so my delta G value pops up as a +2. We know that positive delta G values are not favorable, which is why when we have a positive delta H and a negative delta S, we are usually unfavorable. But let's change it up. Let's see what happens when I switch those signs. So let's take situation 2 down here. If I have a negative delta H value and a positive delta S value. So again, let's make everything equal to 1, but I have a negative delta H value and I have a positive delta S value. Well, in that case, when I work out my math, I have -1 minus 1, which is equal to -2. So in that case, my delta G value pops out negative. So usually those ones are favorable. And so if I were to go through this entire chart, we could see mathematically what specific temperatures might pop out and give our delta G value a negative value or a positive value or whatever. But really, those signs of our delta H and our delta S, they're really controlling whether or not my process is spontaneous. And then temperature is a factor when you have 2 negatives together or 2 positives together. Okay? We're going to do a lot of work with this formula in class, so I'm not really going to spend a lot of time with it right now. What I do want to show you is our calculation of delta G of a reaction in a different way, which is very similar to our calculation of our delta S for a reaction, because it's almost the same exact formula. We see that our delta G of our reaction is equal to the sum of our products minus the sum of our reactants. So again, pretty much the same formula we saw with entropy, products minus reactants. The one thing to note is that if you have an element, meaning O2, N2, like a single element, they have delta G of formation values of 0 kilojoules per mole, so we can go ahead and leave them out of any of the calculations using this formula up here. So that's just one thing to note. So let's take our example here. We have a calculation of the free energy change of the reaction below. So we're seeing 2 nitrogen dioxides rearranging themselves and becoming dinitrogen tetraoxide. Okay, so once again, we're going to do products minus reactants. So we're going to take our N2O4 value, so that's our 9.2 up here, and we're going to subtract our reactant values. So we're going to subtract 2 times our NO2 value, and that's 51.3. And then all I need to do is plug that into my calculator. So I'll take a second to do that. And we get a value of -93.4. In terms of our unit, we always go back to our chart. Our chart says our unit is kilojoules per mole. And so that delta G value popped out negative, meaning that we can analyze that a little bit further, and we know that our process, our reaction, this is favorable. What that means, once again, is that This is very likely to happen at any given temperature without any extra input of energy from the outside. So if you were to try to do this reaction, you would likely not have to heat it or whatever to get it started. All right, if you have any questions, please feel free to ask.